In this lecture, we will learn Michaelis Menten equation. Before going into the derivation of this equation, let us first get familiarized with few of the terminology. Km. Km is the substrate concentration at which an enzyme catalyzed reaction reaches half of its maximum velocity. That is, lower the Km, higher is the affinity of the substrate towards the enzyme. Coming to Vmax, Vmax is the maximum velocity or the rate at which an enzyme catalyzed reaction reaches its peak. Coming to Kcat, Kcat is also known as the turnover number of an enzyme or otherwise catalytic constant or specificity constant. It is the number of the reaction processes or turnovers that each active site of an enzyme catalyzes per unit time or per second. Higher is the ratio of the Kcat Km denotes the efficiency of an enzyme. Kcat by Km undergoes second order constant of the enzymatic reaction. Coming to the derivation of Michaelis-Menten equation, enzyme plus substrate gives enzyme substrate complex, and this enzyme substrate complex further gives products plus enzyme. That is, the enzyme is recovered totally back here. When we take the velocity is the partial derivative of the products divided by dt, that is change in time, that is equal to K2 of enzyme substrate complex. Here K1, K minus 1, K2 are all the rate constants. When we take the derivative of enzyme substrate complex with respect to time, we will get K1 into free enzyme plus substrate minus K minus 1 into ES minus K2 into ES. This reaction gives us the overall rate of the production of the ES complex. Ks is equal to K minus 1 divided by K1. Ks is the dissociation constant. That is, the enzyme substrate complex is dissociated back into the enzyme plus substrate, which is concentration of E into S divided by concentration of ES. This is possible only when the K minus 1 is much greater than the K2. That is, when the ES complex is preferring more towards the dissociation into enzyme plus substrate instead of forming products plus enzyme. Under steady state equation, that is under steady state conditions, when the substrate is highly saturated and no more binds with the enzyme, then derivative of ES complex with respect to time is 0, as no more substrate is binding with the enzyme's active site. Enzyme total, E total is equal to concentration of enzyme plus concentration of enzyme substrate complex. From equations 2, 4 and 5, we can derive that K1 into E total minus ES. K1 is the reaction proceeding towards enzyme substrate complex. E total is the free enzyme plus enzyme substrate complex. So we can write that K into E total minus concentration of ES whole into concentration of substrate is equal to K minus 1 plus K2 of enzyme substrate complex. On rearranging these, and we can get concentration of enzyme into K minus 1. We'll take this expression towards this side and this towards this side. ES concentration of ES into K minus 1 plus K2 plus K1 into substrate. If we expand this equation, then we will get this K1 into S. That is, when we multiply K1 E total and concentration of substrate minus K1 ES complex into S. When this expression goes towards this side, it becomes a positive and makes plus K1 into S is equal to K1 into K1 into E total into substrate. Hope you have understood this. Otherwise, if we and expand this, we can easily get K1 E total into substrate. Here it is. This one goes that side plus K1 into ES is taken outside the bracket common. Substrate is still there. When we divide both the sides with K1 and solve for ES, concentration of enzyme substrate, then we can get E total concentration into substrate concentration divided by Km plus S. This is obtained by when we divide whole of this expression with K1. This K1 and this K1 will get cancelled, and when we have to open the braces, and the expression called K minus 1 plus K2 by K1. Since we have divided with K1, this whole term is represented by Km. E total into concentration of S divided by Km, this whole Km plus concentration of substrate. We can calculate the initial velocity of the reaction from equation 1. V0 is the initial velocity is equal to derivative of products divided by dt at time t is equal to K2 into ES. K2 into ES. Since we got the concentration of ES complex as this, we can substitute in this equation K2 into ET, concentration of total enzyme, into concentration of substrate whole divided by Km plus concentration of substrate. Now we will calculate the Vmax. The maximal velocity of a reaction Vmax occurs at high substrate concentrations. As we have seen previously, when the enzyme is totally saturated and no more substrate is high, and concentration of substrate is high and no more substrate binds with the enzyme, Vmax is equal to K2 into E total. By combining this equation with the previous equation V0, we can get V0 is equal to Vmax into concentration of substrate divided by Km plus concentration of substrate. This is the equation 7 which we got previously. When we combine this equation with this equation, we get the expression V0 is equal to Vmax. Since here it is said that Vmax is equal to K2 into concentration of enzyme total into K2. This is represented with Vmax. Vmax into concentration of substrate divided by Km plus concentration of substrate. This is called as the Michaelis-Menten equation, where we can find out the velocity of the equation or the reaction, velocity of the reaction at any given point of time. Coming to the significance of Michaelis-Menten constant, Km is equal to K minus 1 by K1. K minus 1 is the reaction which is proceeding towards the formation of free enzyme plus substrate from enzyme substrate complex. K1 is the reaction which is proceeding towards the formation of enzyme substrate complex, plus K2. K2 is the reaction proceeding towards products plus enzyme divided by K1. This K minus 1 by K1 is the dissociation constant, Ks. Ks is known to be dissociation constant as it dissociates the enzyme and substrate freely in a reversible reaction, plus K2 by K1. We can write the Lineweaver-Burke plot, draw the Lineweaver-Burke plot. In this, V0 and concentration of substrate are taken in a reciprocal manner. That is why it is known as double reciprocal plot, and this is done only for the convenience of, to calculate the slope, as it forms a linear graph. Whereas the Michaelis-Menten graph gives us a rectangular hyperbola, wherein calculating the slope is difficult in parabolic graphs. Coming here, Lineweaver-Burke plot, this expression is reciprocal. 1 by V naught is equal to Km plus concentration of S whole divided by V max into concentration of S. The reverse of this, if we solve it, we get Km by V max into concentration of S plus concentration of substrate divided by V max into concentration of substrate. These two get cancelled out and will get 1, and it can be rewritten as Km by V max into 1 by substrate concentration plus 1 by V max. This is the same equation of the Lineweaver-Burke plot, exactly the reciprocal of the Michaelis-Menten equation. Catalytic constant or turnover number. As we have discussed in the starting of the video, Kcat is the turnover number of an enzyme, or the number of reactions happening with the enzyme's active site per unit time. Kcat is equal to Vmax by total enzyme. If we calculate Kcat by Km is equal to K2 by Km, that is equal to K1 into K2 by K minus 1 plus K2. Thank you.